Hi, this is Brandon Baines in the Math Department at Lipscomb University, here to talk with you today about the binomial probability formula. In this presentation, you'll learn how to calculate certain probabilities using the binomial probability formula. The binomial probability formula is only for probability experiments that are considered a binomial probability experiment. The characteristics of this type of experiment is that there are n repeated independent trials. Each trial has two possible outcomes that we'll consider. We often use the word success and failure. And for each trial, the probability of success and for failure, and failure for that matter, remains the same. All right, so think about this in repeated trials. Let's start there. What does that mean? This could be in a hospital setting where we're administering some treatment to some new treatment, experimental treatment. The trial would be giving that treatment to patient 1, and then the next trial would be giving that treatment to patient 2, and so on. So we would, however many patients we have or subjects we have there, those would be our trials, and they're independent in that the effect of the drug, if we're going with this drug example here, it's not whether that helps that patient or not. It doesn't affect whether the next patient is helped or not, right? The experiment is for that trial, and it doesn't influence the other trials' outcomes. All right, two possible outcomes. Again, we often use this word success and failure, but you really can just consider any probability experiment that has two outcomes. Then you can call it a binomial, as long as it fits the other characteristics here. You can call it binomial. So flipping a coin, you have two possible outcomes there, heads and tails. Those aren't necessarily a success and failure kind of characterization, but we can still call it binomial because there are two outcomes. All right. For each trial, the probability of success remains the same. That just means that each time we do it, each time we flip a coin, for example, we have the same probability of flipping a coin, flipping a heads, same probability each time you flip a coin. Okay, the binomial probability formula, it looks a little intimidating, but we actually know all of these pieces of this formula already. Again, we're still using this probability notation. This is the probability of X, and in this case, we're talking about obtaining exactly X successes from n independent trials of a binomial probability experiment. The formula here is given by NCX. That should look familiar to us from our counting problems that we worked earlier in this app. This is the sets of size X that we're counting, NCX. In this case, that would be N trials. I like to think of it as choose X successes. And then this is P to the X multiplied by Q to the N minus X. In this case, P is representing the probability of success on a single trial, and Q is the probability of failure, which will be given by 1 minus P. Let's take a look at an example. A light bulb manufacturer has determined that there's a 0.05% chance of producing a defective light bulb. On a given day, the manufacturer produces 1,000 light bulbs. What's the probability that 4 defective light bulbs are produced that day? Part B, what's the probability that at least 1 defective light bulb is produced that day? we examine this scenario, we can see that it is binomial. We have 1,000 independent trials. That is 1,000 light bulbs are produced. So each light bulb being produced is a trial of our experiment. We can see that the probability of success or failure, if we want to consider a defective light bulb a failure, it remains the same. There's a 0.05% chance of producing a defective light bulb. And so we can apply the binomial probability formula to these contexts. So in part A, when we're finding the probability of exactly 4 successes, we would do 1,000 trials. Choose 4 successes multiplied by the probability of a success. In this case, I'm using that language success, but we're really talking about defectives here. So the probability of a defective raised to the 4th power multiplied by the probability of not getting a defective, which is 0.9995, and we're raising that to the 996th power. Important to note here, if we toggle back, the probability that was presented here was 0.05%, and you'll notice in this formula we have used the numeric form 0.0005. We'll generally do that anytime we put a number into a calculation. If it's presented to us as a percent, we'll put the actual numeric form, not the percent form, in the calculation. All right, this product turns out to be 16 ten-thousandths when we round to the nearest 10,000th. On part B, we want the probability of at least 1 defective. Well, if we think at least 1 defective, that means 1 defective, 2 defectives, 3 defectives, and so on. The only defective that we're not counting is the possibility of no defectives. So we can apply that 1 minus the probability of no defectives will give us all of those other probabilities. Well, the probability of 0 defectives using the binomial probability formula is calculated. 1,000 choose 0 defectives multiplied by 0.0005 to the 0th power times 0.9995 to the 1,000th power. That product turns out to be 0.3935, and that's rounded to the nearest 10,000th.